So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Andreas Bluhm from University of Grenoble-Alpes, who will tell us about certifying and learning local quantum Hamiltonians. So Andreas is a research scientist with the French National Center for Scientific Research, working at the Grenoble Computer Science Laboratory. And his main interests are in quantum information theory and quantum spin systems. Some questions he has been interested in answering have been like the entanglement needed to do secure quantum position verification, the most incompatible quantum measurements, and learning properties of unknown quantum many-body systems. And previously, he was a postdoc at QMath in Copenhagen, and he got his PhD from Technical University of Munich. Andreas, the floor is yours.
Thank you. Thanks for the introduction. So as you can see, this is part of the last thing that was mentioned, like the certifying and learning properties of many-body systems. And this is joint work with a lot of people, actually. So together with Matthias Caro, Francisco Escudero Gutierrez, Junso Lee, Adi Ufkir, Kambiz Rosé, and Myung-Jung Shin. So a lot of people involved in this. And if you have any complaints about the talk, you should complain to them that I did a bad job. Right. So the question is like that we want to start with is why do we want to learn and certify many-body systems in the first place, right? So as you are all aware of, I'm sure, is that we are building ever larger quantum devices involving hundreds of qubits to serve, for example, as quantum computers and as simulators, all these kinds of things. And somehow, like when we're building these things, we have to be sure that they function properly, right? And this is what learning and testing of such systems will do. In particular, for example, if you want to do error mitigation, you want to learn the dynamics of the system because, like, you want to do what the device you're doing is actually you have built is actually doing. And so, if you can find out what it's doing, you can somehow fix errors if you find any. And certification has a slightly different idea. So that you usually have an idea like what you wanted to build, right? So the device should have a certain functionality, and certification is needed to make sure that the device works as intended. So you don't want to figure out what it does. You just want to figure out whether it does the thing that you expected it to do. So that's the difference between learning and certification. And we will look at both things in this talk. So let's talk about the access models and relevant figures of merits that will appear in this talk. And the results typically depend a lot on the access model. So in this talk, we will consider two different ones. First one's access to dynamics. So you can somehow like switch the device on and off for a certain amount of time. And the second one is access to thermal equilibrium states or Gibbs states. And the results often also like make additional assumptions about the quantum system at hand, so that we have to watch out for. So for example, locality, sparsity, low intersection. We also will talk about some of those later. And then the figures of merit that are interesting for these kind of questions are, for example, the number of queries. Like number of queries basically means that how often you have to run this experiment, like the quantum part of the experiment. Then the expected total evolution time. I think that's self-explanatory. That's the amount of time it actually you actually need to run this protocol. The classical post-processing time. So like anything that comes after the quantum part. So you want to somehow like classically post-process the results and then compute something like your answer that you want to have. And also the quantum complexity of the input states and output measurements. This basically quantifies how hard it is to actually implement this protocol. So let us start, as I've already mentioned, locality of Hamiltonians is important. So let me start by explaining what that actually is. So we are always in a setting when there's n qubits. So we can expand every operator, in particular every Hamiltonian, in terms of strings of Pauli operators. So these P's here are strings of either identity, Pauli X, Pauli Y, or Pauli Z. And they have all length n. So then these HPs here, these are the coefficients of the Pauli string P. So they are complex numbers, and they are the weights of the Pauli strings. So what does it mean to be local? For example, imagine that you have this term here, like z on the 3rd qubit and z on the 7th qubit. So this would be too local because you're only touching 2 qubits, right? All the other ones are not touched. So like a term in general is k local if it touches at most k qubits. We can make this a bit more formal. So the weight p here is the number of sites where the pi is not the identity, right? So like here it would be like identity on the 1st, identity on the 2nd, z on the 3rd, identity on the 4th, identity on the 5th, identity on the 6th, z on the 7th, identity on the 8th. So there's only 2 things where you were not the identity. This is why it has weight 2. So for example, if you have like x, y, z, then you have weight 3. And if you have z3, that's 7, as the example above, you have weight 2. And then you can say a Hamiltonian is k local if it has the form of the expansion above, but now with the constraint that the weights of the Pauli operators is at most k, right? So note that somehow we are only counting how many qubits we are touching. We are not counting how far away they are. There's no like measure of distance. Think like if there's a measure of distance, if you were saying, okay, like you want 2 local to be everything that is nearest neighbor, then people would often call this geometrically local. So like we are only like interested in like 2 local in the sense of like 2 body interactions. It doesn't really matter how far these things are apart from each other, right? A related notion, or like, is the sparsity of Hamiltonians that will also make its appearance later. So like, what is that? So sparsity counts how many Pauli terms will actually appear in the end. And so like we're looking at the same kind of n-qubit Hamiltonian, and for it, its sparsity is the number s of coefficients with non-zero coefficients. So like a number s of Pauli strings p with non-zero coefficients. So it's all the p's here where the hp, the weight is not 0. So let's make an example. So for example, if your Hamiltonian is this, like 2 times z1 minus x1 z2 plus 3 times x3, this has 3 active terms, right? 3 terms where the coefficients are not 0. So it has sparsity 3. But it's too local, right? Because like the highest interaction here is between 2 sides, the first one and the second one, and that's a 2 local term. So like the whole Hamiltonian is too local, right? So what will we see in this talk? We will actually like look at all the different combinations of access model and learning and certification. And the first one is would be learning from dynamics. So learning from dynamics, I already hinted at that. So we somehow have access to a unitary operator that is e to the minus iht. So like the unitary time evolution under h. The h is unknown, so you want to learn it. So the aim of your algorithm is to output like an h hat, which is an estimator of h that should be reasonably close to h. And it can be learned by querying e to the minus iht for various times t. So like this is somewhat like the control that you have. We will look at this later in more detail. And in opposition to that, like learning from Gibbs states would be that you're given Gibbs states rho h beta, and you want to output an estimator rho hat that is close to this Gibbs state. So this learns directly the Gibbs state from access to copies of the Gibbs state. It doesn't learn the Hamiltonian, it just learns the Gibbs state. Yeah. Actually, we will not talk so much about the first one here because our results are mostly for learning Gibbs states and certifying in the dynamics and Gibbs model. So what does certification mean? Well, certification means that you're given, like if you look at learning from dynamics, certifying from dynamics, that you're given a known H0. So like this is somehow like the functionality that you want to implement, like the thing that your device should be. And you're again giving query access to UH of t, so like the unitary time evolution under H. And you want to output whether they are close or far. So meaning that you want to test whether H and H0 are either close or far. And for the Gibbs state, that's more or less the same thing, but here you're given Gibbs states for H and H0, and you also want to output whether those are close or far. So you want to test whether the corresponding thermal states from H and H0 are close or far. Same idea, like somehow you have a thermal state of H0 that you want to produce, and you want to know whether you have succeeded in doing that. That's why it's called certification. So as I said, like learning wants to figure out what an unknown device does, and certification wants to test whether it behaves as expected. That's the thing to remember here. Okay, let us start with the first thing. And so we will start with the access to dynamics model, and we will talk about certification in this model. So a bit more details on the access to dynamics. So the idea is really you have an unknown quantum system here. You can switch it on and switch it off. So you can control how long the time evolution should run, but you don't know what it is. And you're able to prepare a quantum input state and measure it afterwards. And the algorithm will prepare suitable states, let them evolve under H for some time t, then perform a measurement and like classically post-processing the results. So in other words, we can apply this unitary here for a time of our choosing. And we assume a bit more, actually. We assume that we have coherent access, so we can do this several times before we have to measure. So we can run the time evolution for different times and do something quantum in between. So like as a circuit looks like this. So if your state on n qubits, you can run the time evolution for time t1. Then you can do some intervention or some control, like any unitary or like any quantum circuit v1. Then you can run the experiment again for a time t2, then have another quantum circuit and so on until you in the end you measure. And then you can still like classically process if you want. And the figure of merit that we will be most concerned with is total evolution time. So like the total evolution time is the sum of all these ti's here. So t1 plus t2 until tn. Right? So really like the time that we run the experiment for. So what is our result here? Well, our first main result is optimal k-local Hamiltonian certification if k is constant. So you're given h and h0 two n qubit k-local traceless Hamiltonians. So like where k is assumed to be constant. Traceless is like because like if the Hamiltonian was not traceless, there would be like a term proportional to the identity, right? And this identity term is just a phase. So that's unobservable. That's why we say like all the Hamiltonians are traceless to get rid of this unobservable degree of freedom. So now assume that H0 is known in advance. Then there's an algorithm with access to the classical description of H0. So like this is the one that you know in advance. And to the time evolution of H. So H you don't know, you can just like switch it on or off the device. That uses 1 over epsilon total evolution time to determine whether either H and H0 are close in this normalized Frobenius distance, or they are far, they are bigger than epsilon with high probability. Right, so you want to know whether either they are almost the same or they are very different. And in fact, like we prove the upper bound for this. So like we give an algorithm that does that. And the lower bound of 1 over epsilon that actually comes from distinguishing the Hamiltonians H equals to epsilon x and H0 equals to minus epsilon x. So like this gives you a lower bound that has been known before. And for a Hamiltonian that looks like this, right, that is expanded in terms of local Pauli strings, this normalized Frobenius norm is defined basically as the L2 norm of these coefficient HP here. So like the usual Euclidean norm. It's the same as like the usual Frobenius norm distance, just like you divide by 1 over the square root of the dimension. So we will also see this later. So what has been done previously? How does it compare to what people have done previously? And like, okay, as again, like we are looking at the total evolution time as a figure of merit. There's like different figures of merit that we will not consider at the moment. And so like if you look at certification, then the previous best was either of order s to the 3k divided by 2 divided by epsilon. So there's also 1 over epsilon scaling if your Hamiltonian is sparse. That's from this paper down here. Or 1 over epsilon squared, which is from this paper down here. So, and what we get is like for constant k, well, I mean, like this gives 1 over epsilon. And in general, like it looks like constant to the k divided by epsilon. So it improves over these previous things if you have a non-sparse Hamiltonian. So like the main message, as I said, is like that for constant locality k, like the certification is optimal because if this 1 over epsilon lower bound, now we have a 1 over epsilon algorithm. So like we know what is the best algorithm to do certification in the access from dynamics model. So like now I want to take a lot of time to go through the proof sketch because I think like there's some ideas that you maybe also want to incorporate in your research or that it would be good to know about. So we will first write delta H as the difference between H and H0, right? Just like to reformulate the problem a bit. And if H is actually equal to H0, then the delta H is 0. And if h is far from h0, then delta h should have like non-zero energy differences. That's the idea. So in other words, our aim is to distinguish whether either this delta h is 0 or whether like the normalized Frobenius norm of delta h is bigger than epsilon. You might note that like the theorem before was a bit different. So like we didn't have 0 here. We had like a small thing here, which was like epsilon divided by something. But for the proof idea, that's a bit easier to just assume that we want to like do a non-tolerant testing. So like that this is actually 0 or non-zero. Because the simpler problems already explains the idea. And then in the end, you just have to make sure that everything works if the difference here is not 0, but small. So the first ingredient that we want to consider is trotterization. So our experiments will use the time evolution of the difference Hamiltonian delta H here. But then the question is, like, how do we get that? Because like we don't have the time evolution under H0. I mean, you can implement it ourselves. But in principle, our unknown device only gives us the time evolution with respect to h. So how do we get access to the time evolution under delta h? And the idea is to use product formula, so trotterization. So it's known that you can always write the evolution of delta h like this, as a product of the time evolution of h that we have access to and h0. And since we know like that h0 is known in advance, this is something we can implement ourselves as a control, right? Remember that we had the access model that we have, this coherent access model was always like run the time evolution for some time, then do some control, then run it for another time. And this is exactly of this form. So we can just assume that we have access to the dynamics of delta H and work with that. So this is out of the way. And then the next ingredient that we want to use is Bell sampling. So conceptually, Bell sampling is Fourier sampling where the basis functions are Pauli operators. What does that mean? So imagine you're given a unitary and that you can also like expand in terms of Pauli strings. And now you want to somehow measure this U or sample from the U such that the probability of obtaining the answer P, where P is a Pauli string, should be given with like this coefficient here, UP squared. So in the circuit that does this looks like this. So you prepare n Bell pairs. You run the U on half of the Bell pairs, or like half of the qubits of the Bell pairs, like n qubits. Then you do a Bell basis measurement, and this will give you like an n qubit Pauli string P with exactly the right probability. And if we want to do certification, then we have to use this U as the unitary time operator of delta H. And this formal algorithm like estimates the identity probability of like the probability of getting identity UI squared without quantum memory. Sorry, like the thing that I showed here uses quantum memory, right? Because like you need these n additional qubits, but like the algorithm that we will run in the end, that doesn't need this additional quantum memory. So there's a way to get around this. But sort of Bell sampling is the idea, although we don't use the exact implementation that I've shown here. And we're only interested in getting the outcome identity, as I will show next. So remember, if h is equals to h0, then delta h is 0. And if the unitary, and in this case, the unitary e to the minus it delta h is the identity, right? So if you do Bell sampling, you will always get the identity Pauli string from this, because there's nothing else, right? I mean, there's no other weights here. So if h is h0, you always get an identity outcome. And if h is far from h0, non-identity appears. So as soon as you measure non-identity, then you know that h must be far from h0. So what we want to do is we want to estimate the probability of seeing a non-identity Pauli string. And then if it's high enough, we can sort of design our algorithm. But let me first give you the algorithm, because now the ideas are clear. That's what I want to do. So we want to repeat the following for a constant number of times. We want to pick a random waiting time, or like a random time for which we run the experiment between 0 and 2 over epsilon. Then we want to implement an approximation of e to the minus it delta h using these product formulas, as I've already shown. Then we want to estimate the identity probability for this unitary here of this difference time evolution. And if the identity probability is noticeably below 1, then we output far, right? Because like this should never happen, right? You should never see anything that is not the identity if you're in the close case, and then we abort. And if that doesn't happen, we've done this enough number of times, then we just output close, because we never see that anything other than the identity happens. So therefore it must be close. And okay, you have to prove that it works, but this will come to in a minute. And the total evolution time that you get from this is of order 9 to the 2k log 1 over delta divided by epsilon. So this is exactly this constant to the k divided by epsilon scaling that I was mentioning before. And for constant k, this is optimal. So now we have to.
Sorry, can I just ask?
Sure.
Why do you need to choose the wait times randomly? Is that essential?
Yes, this will come. This will come. This will now come on the next slide, I think, even because
okay.
somehow we have to optimize. We have to estimate what this probability here is, right? In the case where I have delta h far, right? I mean, it works if the delta h is 0, then you can just measure whatever. But you need to be sure that somehow you're seeing the difference. And if you would take, for example, t equals to 0, of course, then you would see no difference, because the e to the minus it delta h would then also be the identity, right? So you somehow have to let this run for long enough, and random will help you here. But thanks for the question.
I mean, I guess I was just asking, maybe you could fix it to some number in between, but that's also not good.
Yeah, exactly. You will see on the next slide that the result that we are using here by Tong and Sinya that wants a random waiting time.
Okay, I see.
Okay. Yeah. If it is not clear on the next 2 slides, then ask me again. Okay, thanks. It's good to see that people are listening, because I don't see anyone. Right. Okay, so then we come to the result that I was already teasering. So we can create the e to the minus delta ht unitary. And now we want to use this lemma here. It's a lemma from Sinya and Tong, as I was saying. And they have proven that the probability of Bell sampling I from e to the minus I delta ht can be represented like this. So this is the probability here. And it's like a sum of cosines of the difference of eigenvalues of delta h normalized. And we can use this now to have because we need to estimate this. And for this, the figure of merit that is important is this number of eigenvalues that are actually far, right? So this lambda up to normalization here tells you how many eigenvalue pairs there are that are far apart. These are the ones that you can see if delta h is big, right? And then we have this lemma here that explains why you need random times. So if you suppose that you have somehow a lower bound on this quantity here for LH or delta H in the end, then there's a randomized procedure that uses order of log 1 over delta samples of IIT, this identity probability for uniformly random t. And then among these random times, it will find a time satisfying that I is smaller equal than 1 minus delta divided by 4, with probability at least 1 minus delta, right? So this random sampling here tells you if you know that there are a lot of different terms here, then you will be far from 1. The probability of getting identity will be far from 1. And this means basically that the algorithm that I've shown before works. Right, this is the reason for the random times. I will not show you the proof of this. This is in the paper, but this is one of the main tools here. So what remains there to do? So imagine that now you knew somehow that if you are in the far case, so if you're in the case where delta H, a normalized Frobenius norm, is bigger or equal than epsilon, that then this lambda is always bounded below by a constant, then you would be done, because then you could distinguish using this lemma delta H equals to 0 and delta H big using time evolution, total evolution time 1 over epsilon, because then this algorithm that I showed before just works, because you will see at some point that the probability of getting identity is below 1, right? So this is what we have to show. Now we have to show that if we are in the far case, then this lambda here is bounded below by a constant. That's what we have to prove. If we have proven that, then we are done. So how do we do that? And now we are also using a trick from probabilities, right? So like if we express f of s and t as the difference of eigenvalues, so like different of eigenvalue s and eigenvalue t, then we can write this lambda, like the number of faraway eigenvalues, as the probability over t and s, where t and s are uniform, of the absolute value of this s being f being lower bounded by delta h, right? So therefore we need a tail bound. And as a tail bound, we can use the Paley-Sigmund inequality, which states that if you have like a random variable f, then probability that f squared is bigger or equal than 1/2 the expectation value of f squared is lower bounded by the second moment of f and the fourth moment of f. So this is what we have to control now. So let's do that. So as I said, like we want to calculate the second moment of f and the fourth moment of f, for f like being the difference of eigenvalues. And the second moment of f is just like 2 times delta h in this 2 norm here. And like the 2 norm means it's like the normalized Schatten p norm. Like that's the p norm we consider here. As I said, like divided by 1 over the dimension. So here, like the 2 norm is the normalized Frobenius norm that we want. So this is good. Like this will be lower bounded by epsilon squared, or like 2 epsilon squared. That's good. But now, like in the fourth moment, we also have this 4 norm here. And the 4 norm we a priori don't have like a control over. So we have to do something about this. 2 norm here is good. That's what we want. And now we're using that delta h is k local, because then we can use hypercontractivity or a quantum version of Bonami's lemma that has been proven in this paper down here. Then this tells you that here, if you are in the k local setting, then the 4 norm to the 4th is upper bounded by 9 to the k, so where the k is the locality, times the 2 norm of delta h to the 4, right? So like we can replace this 4 norm that we don't like by a 2 norm that we do like. Right, and if we have done that, then we can use this to prove that delta h, the normalized Frobenius norm of that, if it's lower bounded by epsilon, then like the lambda here is lower bounded by 9 to the minus k. And if k is constant, that's a constant. So this is what we want to do. We wanted to do like the lambda is lower bounded by a constant for constant k, and then we are done with the proof. That finished the proof sketch. Right? So this was everything I wanted to tell you about the certification from Gibbs axis. For the learning from Gibbs, for the certification from unitary time evolution axis. For the learning from access to dynamics, we don't have any new results. So the remainder of the talk will be about certification and learning from access to Gibbs states. So let us start again with the axis model. So in the Gibbs axis model, we do not control the time evolution. So we cannot we don't have a device that we can turn on and turn off, but we have Gibbs states. Gibbs states, as you would probably, surely know, like they look like this. So like you have a beta here, and they are like e to the minus beta h divided by its trace. Beta is real. And each, like we get copies here of this state, and each copy is measured once, and usually with a simple Pauli measurement. We will go to the details later. And this beta here is the inverse temperature. It's like 1 over Boltzmann constant times temperature. So larger beta here means lower temperature, right? That's why people always call the beta the inverse temperature. So like, what is the cost we want to consider? Before we had total time evolution. Here, that doesn't really make sense anymore. So what we're looking at is the sample cost, meaning like the number of copies that we need to measure. And like the learning uses copies of row h, because there's just one h, right? The h we want to learn. And the certification uses copies both of row h and row h0. So like before, like in the learning from access to dynamics, the h0 was somewhat classical, and we could just use this knowledge. And here we just get Gibbs states for h and h0, but we somehow know what h0 is. We just want to know whether they're close or not. So like the h0 is somewhat the reference state we want to test against. So what is which accuracy do we want? Before we had like a normalized Frobenius norm. This for like this setting, this is not natural. So here the natural distance is the trace norm. So we wanted to look at the trace norm between row h and row h0 as to decide the close and far cases. And this is just like the trace of the modulus of rho minus sigma. Right. So let's look at what other people have done before us. So previously, I mean, we're not the first ones to do this, obviously, right? To learn Gibbs states. But previously, people always tried like a harder route. So they were always taking a Gibbs state, then you're running an algorithm to learn the Hamiltonian for this, and then use this learned Hamiltonian to like estimate the Gibbs state for this learned Hamiltonian. But the problem is that this route can be, or is like actually is exponential in beta, as we will see later. So if you want to get around this, you have to do something smarter or something different. So as I said, like for the learning and the certification from Gibbs state, previously you always got bounds exponential in beta. And this work gets around this. So like this work says, okay, we get polynomial samples for learning in beta. And for certification, we get polynomial samples and time in beta. So in particular, for learning, we will get like poly n beta squared over epsilon to the 4 samples. For certification, the same sample size and also like a polynomial running time. So the learning actually is not, the running time is actually not efficient. We will also see this later. So let us start with the Hamiltonian. Yes.
Just to clarify, I guess it's implied by what you're showing. So the samples are actually, the beta is fixed already at the beginning.
Yes, yes, the beta is always fixed. That's true. Yeah, you can somewhat see. Imagine that your experiment has a fixed temperature, right? Sort of it's a room temperature or something. Yeah. You cannot control the beta. Otherwise, like it would be more like learning from dynamics. But this is also like an interesting setting actually that we haven't considered.
Okay.
Right. Thanks for the question. So let us start with the Hamiltonian learning from Gibbs states. So let rho h beta be the Gibbs state of an unknown n-qubit Hamiltonian h. Local means also k local here, right? So like as before. At temperature beta with like all the coefficients of the Pauli strings upper bounded by 1 for every p. This is like a normalization. That's somewhat like you don't get like infinite energy basically. So then there's an algorithm that with high probability epsilon learns rho h, so like up to like trace norm epsilon, using this number of like poly n beta squared divided by epsilon to the 4 single copies of the states. So you don't need to do any collective measurements. You only like just measure copy 1 by 1. And as a word of warning, like our algorithm is not time efficient. That's like an open question that I will ask in the end. And it's actually important to avoid learning the Hamiltonian. So like we just learn directly the Gibbs state because the people have proven an order of e to the beta lower bound on the sample complexity for learning. That's in this paper down here. So if you try to learn the Hamiltonian first, then you will never end up with a guarantee of this form. So again, like what's the strategy for this result? And the main thing that I want to use in the remainder of this talk are bounds like this. So you're interested in somewhere like the difference of two different local Hamiltonians, right? Or their Gibbs states in trace distance. And you can upper bound them like this, where you have the difference of Gibbs states and the difference of Hamiltonians appearing. And you can also write it out, since you're k local, in terms of the coefficients here. So like the maximum of the coefficients. So like if the coefficients are not very different, then the states cannot be very different either, which is natural, right? So here's what we want to do. We want to build a finite candidate set of possible thermal states that sort of could be the state that we are learning. And then we want to measure many simple local Pauli measurements from copies of rho of the Gibbs state. And then we want to use these measurement outcomes to choose or certify the matching thermal states among this candidate set here. So we get copies, we measure, and then we find the thermal state. That's a very easy prescription. So, and the main tool that we are going to use here to make our samples efficient, like the sample number efficient, are classical shadows that have been invented by Huang, Qing, and Presco. So I will just briefly like give you the idea in case you don't know it. I think probably most of you know it. So like suppose we have known observables O1 to OM, and we want all expectation values with respect to a fixed state here, which now we will call mu I, for all the observables at the same time. Then there's a good way to do it, which are these classical shadows. So you can randomize single copy randomized single copy measurements, and these let one estimate many simple observables at the same time. So like get estimators mu I hat that are close to the expectation value simultaneously for all I that you want by only using log m divided by epsilon squared samples. So much less than the m that otherwise you would have needed to measure. And like, notice that I said simple observable, so that doesn't work for any observable, but simple in this case includes k local observables for a constant k. So like in the paper, it's specified by like some kind of shadow norm, but like we are only having k local observables, and for these that works. So we can use shadows. So what we want to do is like we have our copies of rho. We want to have the measure shadow data or get shadow data, and then estimate all local Pauli statistics at the same time. And yeah, the log m is going to help us here. Right. So let's go to the proof sketch. This will be much shorter than the proof sketch for the certification in the dynamic access model. So this formula I've already shown you, and now we want to use it because now we can build an epsilon net of Gibbs states. And this epsilon net we call S eta. These are all the Gibbs states that come from Hamiltonians and also some net H eta. And H eta here are k local Hamiltonians with fixed HPs here. So HPs, we say, okay, like we take eta times the integers and we confine ourselves to the interval between -1 and 1, because we have this guarantee that like in the Hamiltonian that we want to learn, all the HPs are upper bounded in modulus by 1, right? So they have to lie between -1 and 1. And that's an epsilon covering net of the set of k local Gibbs states when we take, if we take eta of the order epsilon divided by beta to the n to the k times n to the k. So epsilon net means in this case, like if you take any Gibbs state of the Gibbs state that you could learn, then like one element of this S eta will be in distance and trace distance at most epsilon, right? So you've sort of discretized the set of possible states that you could look at. So you just have to find the right one among this net. But this epsilon net is huge, right? I mean, this is exponential size, and this is why our algorithm is not efficient. So because you have to search through all this epsilon net. So this takes too long time. But it is sample efficient, and now we look at that. So the observation here is that if you take now two elements of this epsilon net, because they're both k local, the difference will also be k local, right? So you can also expand it in this way for some coefficients alpha. And hence we can use classical shadows. Like if we use classical shadows, then we can simultaneously obtain accurate estimates of trace of rho h minus h prime, right? Because like h minus h prime is just Pauli. So like if we can estimate all the expectation values for these Pauli strings, we know the alpha p's here, then like we can also get this. And this is, we can get in a sample efficient manner where rho is the state to be learned. So this is what we use our copies for. And then the rest of the proof is to show that the following works. So we have this delta h here. We want to maximize the distance between that and rho prime h minus h prime, right? I mean, like rho prime h and h prime are all from this net. So like these things we can just compute ourselves. We don't have to run any quantum experiments for that. And then we want to find the arcmin of rho prime of this quantity here. So like the claim is, if you have done that, if you have someone like fit the best fit for this quantity here, then like the difference between the estimator and the original Gibbs state is at most epsilon with high probability. And we are making use of this inequality here. So like where the first thing, like this rho and h and h minus h and h prime is this delta h prime, and the rho h prime h minus h prime is what appears here, right? So we're somehow making this small. And if this is small, someone like if we found the state that this makes this the smallest, this is a good estimator for this trace distance here. This you have to prove, of course, but that's the idea. Right. So this closes the learning of Gibbs states, and this brings me to the last topic of today's lecture, today's talk, which is the certification of Gibbs states. So there the theorem is the following. So let rho h and rho h0 at beta be Gibbs states of an n local Hamiltonian, n qubit local Hamiltonian h and h0 at inverse temperature beta, again with hp and h0p upper bounded by 1 for every p. So like the coefficients are again of modulus at most 1. Then there's an algorithm that with high probability decides whether either the Gibbs states are equal of h and h0, or the trace norm distance is bigger or equal than epsilon. And this also, again, uses Pauli and n beta squared divided by epsilon to the 4 single copies of the states. And this algorithm is actually time efficient, right? The learning algorithm was not time efficient. So here we are not using any epsilon nets. And it's time efficient in every parameter. And this answers an open question posed by Anshu in this article here. So let us give a very brief proof sketch here, because this is drawing to an end. So certification has this target Gibbs state of rho 0, and we receive copies of rho and rho 0, right? So what we can, of course, do is we can write the Pauli coefficients of rho p as 1 over 2 to the n trace p rho p rho. And the idea is if the two bounded local Gibbs states are far, then some local Pauli coefficients must be noticeably different, right? So if the trace distance between rho and rho 0 is at least 2 epsilon, then there must be a Pauli string with low weight, because they're both k-local, such that 2 to the n rho p minus rho 0 p is bigger or equal than epsilon squared to the divided by beta to the n to the k. That's not completely obvious because the Hamiltonians are k-local, not the states themselves, but this you can prove using a similar formula as above. For example, this rho beta minus rho prime beta in trace norm is upper bounded by this here. But now, before, you had the Pauli coefficients of the Hamiltonians appearing, but now I have the Pauli coefficients of the Gibbs states, and I only have weight at most k, right? So if I know that these are small, then I know that this thing is small. And conversely, if the difference is big, then there must be one of these coefficient differences that is big. So that's the main insight here. So the algorithm, therefore, is that we are using classical shadows on the copies of rho. We are also using classical shadows on the copies of rho 0. So we can estimate the Pauli coefficients for rho and rho 0 for every piece of weight at most k. And then if some estimated coefficient gap here exceeds 3 epsilon squared divided by 400 beta n to the k, so if this is big, then we output far. And otherwise, if we don't find such a gap, then the output is close, right? This uses the idea that somehow if the states are far apart, then this gap must be close. So if we don't, it must be big. So if we don't find a big gap, then the states must be close. Actually, I've written the theorem that in a non-tolerant way, where we're comparing either rho equals to rho 0 against rho far from rho 0, but it's actually tolerant. So you can allow for the small difference in rho and rho 0, and the algorithm still works. But it's here of order of epsilon squared. So it's much smaller than epsilon. Okay, so this brings me to the end of the results. What are the open questions that you should work on if you liked it and you want to also work on this topic? Well, the first question is about the optimal certification from dynamics. Because if you remember the first result that I showed you, this used heavily the locality of the Hamiltonian. And the question is whether you can still give an optimal certification algorithm if your Hamiltonian is not local. Or you can prove the opposite, right? That locality is needed for this kind of scaling. So that's an interesting open question. Then the learning algorithm for learning from Gibbs states that I've shown you is not time efficient. So the question is to find an algorithm that is both sample and time efficient. The next question is the algorithm for the certification of Gibbs states optimal, right? I mean, we found an efficient algorithm, but we don't know whether it's the best one you could have or whether you can have better ones. And the question is also whether these ideas that we have used for learning and certification somehow translate to other problems. So can you do maybe optimal sparsity testing with them, or can you do optimal locality testing where you want to know whether a Hamiltonian is k-local or not? And of course, we've only looked at unitary dynamics, so maybe you can also do it for dissipative dynamics generated by a Lindblad operator instead of a Hamiltonian. Let me summarize this talk. So we've seen that certifying a local Hamiltonian in normalized Frobenius norm via access to its time evolution can be achieved with only 1 over epsilon evolution time. We have seen that this is optimal because it matches this Heisenberg-scaling lower bound of 1 over epsilon. We have designed an algorithm for learning Gibbs states of local Hamiltonians in trace norm that is sample efficient in all relevant parameters. The previous approaches were exponential in the inverse temperature beta, so we can do better than that because we passed by the need to learn the Hamiltonian. We have also given an algorithm for certifying Gibbs states of local Hamiltonians in trace norm, and that was both sample and time efficient in all relevant parameters. And yeah, this also shows that certification can be much more efficient than Hamiltonian learning. Okay, that's it. If you have any more questions, then now's a good time to ask them. Thanks for listening.
Right. Yeah, thank you very much for giving this very splendid and organized talk. Yeah, so I think we have yeah, a bit of time. Yeah, we probably have like 7 minutes for questions and comments. So anyone who has comments or questions, please feel free to unmute yourself and ask them now. Seeing anyone who's okay, maybe I can start first. So in the last part that you have, I think you mentioned again this certification of the Gibbs state. Like part, I don't know how essential it is. Like you were saying that there should be, if they're far, then there should be coefficients that are like very different. But I mean, I can imagine that you have something where there's small differences in every coefficient, and then they will be far if you kind of like the sum total of all of those small differences. Wouldn't that be possible? That could happen.
No, right? Because like this is what we prove, right? I mean, we prove that. I mean,
oh, okay. So like you rule out this possibility essentially.
Yeah, I mean, like, I mean, there's this 2 to the n factor, right? I mean, this might be very big. So like, it might still be that the difference is small, but it cannot be too small, right? So we have a control of this. So if the trace norm is at least 2 epsilon, then we know how far, like how close they can maximally be or minimally be, and that this is why this algorithm works. But yeah, this is right. I mean, this is like the essential observation that this doesn't happen. Otherwise, this wouldn't work. Yeah. But again, for this we use the k-locality, right? So like, if the states are not k-local, then exactly it can happen what you described, that they can be very close. So the algorithm no longer works.
I see. Okay. Let me see if there's anyone else who had some questions. Right. I don't see anyone. Kind of like a maybe naive question from me. Like, so a lot of these results kind of like, yeah, when you talk about this access model, then you're saying that I guess it's kind of like idealized. So I can perform this experiment and I know exactly what I will get. I have these perfect samples. So I was always curious, like, what happens if you now have some noisy kind of access? How much of these kind of results are like retained?
I mean, like in principle, like this tolerance statements, right, where you say like you do certification either like close, like up to maybe epsilon or bigger than 2 epsilon or something like that. They like deal a bit with this noise question, right? Because like you're not required to have exactly the right functionality, but it just has to be close enough. Or like, and I think it doesn't really matter whether the error comes from the state or the measurement. I guess you can just trade it off. Yeah, but it's interesting.
Yeah, like the algorithm doesn't really see where the error comes from, I guess.
I think so. I think you should take this with a grain of salt, but I think in principle, this gives you some kind of tolerance to imperfections. And the H0 in this, at least like in the certification of the dynamic model, that was classical, right? So there's no errors there.
Yeah.
But I don't remember whether we looked more into this, but yeah, I think it's a relevant question to see like exactly what kinds of experimental errors you could have, and how they affect these kind of algorithms. It's true.